electric field. There is a velocity with which the electron moves known as the drift velocity, and we got the formula of drift velocity. Uh, we have drift velocity v suffix t. The formula of drift velocity is charge on electron into electric field into relaxation time divided by mass of electron. A is charge on electron. This is applied electric field. Applied electric field, and tau is the average relaxation time, and I am just saying relaxation time. Relaxation time, and m is the mass of electron. Mass of electron. So this was the formula we have derived in the earlier class. So today we will define a relation between the current and the drift velocity. Relation between current and drift velocity. Drift velocity. So for this, I am taking a conductor, cylindrical conductor. This is the cylindrical conductor. Okay. And this is the cross section area of the conductor. A is the cross section area. Cross section area of conductor. And I am taking L as the length of conductor. This is L is the length of conductor. Okay, length of the conductor, and we have to define a relation between the current and the drift velocity. So please see here carefully. I am just calculating the volume of this, and we know that volume is area into length. So the volume is equal to area A, area of cross section into length. This is the volume of this conductor. And if in this conductor, small n, now there is a term small n is the number of free electrons per unit volume of conductor. Means n is the number of free electrons in the conductor in the unit volume. Unit volume means 1 meter cube or 1 centimeter cube. The amount of free electrons. And we know that charge on electron is this. I have represented charge on electron as E, as the charge on electron. So suppose from this cross section delta Q charge is flowing. Delta Q is a charge. Delta Q charge is flowing in delta T time. Delta Q charge flowing through the cross section in time delta T. We have discussed this earlier also. So if I want to find the current, then current will be here average current, and current will be delta Q by delta T. We have this. For finding the charge, for finding the charge flowing from this cross section, charge let's say delta q will be small n into volume, total amount of charge, and n is the number of electron per unit volume. From the unitary method you can calculate this. In unit volume, if there are n number of electrons, then in whole volume there are n into volume of electron. Got my point? Suppose the volume of this, I am supposing 5 meter cube. 5 meter cube is the volume of this conductor, and I am saying in 1 meter cube there are n electron. So in 5 meter cube there will be 5 n electron. There will be 5 n electron, means I am multiplying volume with n. Here also I have multiplied volume with n. So delta q is equal to, this is n number of electron in a unit volume, and we have calculated volume area into L. We have calculated volume also. And one thing more, I have not written here, and we are calculating these are the NaL is the total number of I'm just changing it. For calculating the charge delta Q, we have to first calculate the total number of electrons. This N is the total number. This is the capital N. This is the capital N. The total number of electron. N is the number of free electrons in a unit volume, and total N is the total number of electron in total volume. So I have just applied the unitary method. N is equal to total number of electrons. Total number of electron or free electron. Total number of free electrons. In 1 meter cube, if there are n electron, then in 5 meter cube there are 5 n electron. Here n is the total number of electron. So if I want how much charge is flowing, then if I want how much charge is flowing, then I will multiply the total number of electron and charge on electron. Total number of electron is n and charge on electron is E. As you can imagine this like this. From here, if five electrons are passing from this cross section, so how much amount of charge is passing? 5e charge. Okay. If n electron is passing, if 5 electrons is passing from this cross section, the charge will be 5e electron is passing from this cross section. Similarly, if there are n total number of n electron is passing from the cross section, then the amount of charge passing from the cross section is Ne, and N is given by NaL, and this is E, and we know that current is equal to delta Q by delta T. Current is delta Q by delta T, and delta Q is given as, I am writing it, NaLe divided by delta T. But we know that speed is equal to distance upon time, or you can say L upon delta T is the magnitude of drift velocity. Drift velocity, the magnitude of drift velocity. This is the drift velocity, L upon delta T. L is the distance. L is the distance, means length of the conductor. Length of the conductor, and delta T is the time, means the electron is traveling the L length in delta T time. So this will become the drift velocity. So I can write I is equal to, from here A, Na E Ly delta T, and I is equal to Na E Ly delta T is drift velocity, and we know the formula of drift velocity. Na drift velocity is charge on electron, electric field divided by uh, mass of electron, tau, and mass of electron. And if I am saying here is a conductor, and this conductor is connected to the battery whose potential difference is V, whose potential difference, this is the potential difference or voltage, potential difference or voltage, and L is the length of conductor, L is the length of conductor, then the electric field generated is given by, electric field is equal to potential difference divided by N. This is the case. We have defined this. This came from the E is equal to minus dV by dx or dr, you can say. Okay, so this is the thing you should remember. Means this is the potential difference across the ends of conductor. V is the potential difference across the ends of the conductor. L is the length, and E is the electric field generated due to this potential difference. So you can say electric field can be written as V by L. So I okay. So this is the first relation. This is the first relation between current and the drift velocity. Between the current and the drift velocity. Okay. So please note it down till here, and after that we will discuss. Otherwise, you will get confused. Please note it down. So, relation between the current and the drift velocity.
Yes, sir, finish.
Okay. All of you, please note it down. And
Yes,
after that,
sir.
written completely. All of you.
Yes, sir.
Yes, sir.
Nawal, you also.
Yes, sir.
Written. Very good. So now,
One second,
please,
sir. Can you scroll up?
yeah. Now see the relation between the electric field and the potential difference. This will be very useful when we will write the Ohm's law in the next topic. We all know the Ohm's law. What is Ohm's law? But I will write today Ohm's law in some different form in terms of NAE drift velocity. We know Ohm's law is potential difference across the ends of the conductor is directly proportional to the current if temperature and other quantities are constant. But today we will discuss Ohm's law along with this in a different way also. So this point you should remember. I think. So this is a simple derivation. First, you have to calculate the total number of electrons in the conductor. And after that, total amount of charge. Done. Matthew completed.
Yes.
Okay, so I am. This is the relation you have to remember. Please remember this relation. Relation between current I is the current, and drift velocity is V suffix D. This is the relation. And here n is the, I am writing again, n is the number of free electrons per unit volume. Per unit volume. A is the area of cross section. E is the magnitude of charge on electron. V suffix d is the drift velocity, magnitude of drift velocity. You should remember all the terms here. I is equal to NaEVD. And I will write this I is equal to ANEVD because I have learned this formula in this form. From the 12th class, I am writing this formula like this. I is equal to ANEVD. You can write as you want. Okay, so no problem. So now the topic is the Ohm's law. We all know the Ohm's law, very famous law. Ohm's law. So Ohm's law is if temperature and other physical conditions like other physics, and we are talking about the conductor like length and you can say number density of electron, number of electrons per unit volume, etc. are constant, then potential difference across ends of conductor is directly proportional to the current flowing. And please remember, this is not Ohm's law. You cannot say potential difference across the conductor is directly proportional to current is Ohm's law. No, you have to add this statement also. Without this statement, this is not the Ohm's law, because the potential difference is not directly proportional to current every time. This is only true when the temperature and the other physical condition like length and the number density of electron will be constant. I will prove this after certain period of time. So potential difference across the ends of the conductor means I am saying like this is the conductor and a battery is connected to the conductor, and V is the potential difference. V is the potential difference across the ends of the conductor, and I is the current flowing. Current is flowing from positive to negative, and it return back to the negative terminal. So I can say V is directly proportional to I. I is current, V is potential difference. And this, when you remove this proportionality sign, you will get a constant R. R is a constant here. R is constant here, and this R is known as the resistance. R is known as the resistance of conductor or wire. R is the term, and generally we write Ohm's law V is equal to IR. But you cannot say this only this thing is Ohm's law. V is equal to IR is not Ohm's law. Ohm's, you have to say along with this V is equal to IR, and you also add this statement if the temperature and the other physical condition like length and this are constant, V is equal to IR. But generally we study the cases where the temperature and the physical conditions remain same. Like you can take the example of this wire. In this wire, now see here, I am sitting in this room. I am sitting in this room. The temperature of, you can consider the temperature of the room is constant. Temperature of the room constant, and depends on the material, and here the material is also constant. Material is not changing in this wire. Area of cross section is not changing in this wire. So for the conductors, the Ohm's law is valid mostly. So and we when we will draw the graph of Ohm's law, means current potential versus current graph, potential, not potential difference versus current graph of potential difference versus current. So you will get a straight line graph. You will get a straight line graph passing from the origin. Straight line. This line can be like this also, as this also, depending upon the material. But so this is the graph of this V is the potential difference across the ends of conductor. V is the potential difference across the ends of conductor. I is the current flowing in the conductor, and slope of this graph will give you the resistance. Slope is equal to tan theta, means this is the, you will get a straight line, and this straight line will making an angle theta, and if you will take the tan of that theta, you will get the slope, and the slope is the resistance. R is the resistance. And please remember, V is the potential difference, not the potential. Potential difference. And I is the current. I is the current. And here you can say that V versus I graph, the graph of V versus I is a straight line. The graph of V versus I is a straight line. This is very famous graph. Straight line. And I can also prove this with the help of the equation of line, but I am not doing this right now. So please note it down. And Ohm's law is not the only, you can say, potential difference is directly proportional to current. You have to add, if the temperature and other physical conditions remain same, then if the potential difference across the ends of the conductor is directly proportional to current, then this is the Ohm's law.
Sir, can you scroll down?
Guys, other guys.
Yeah, finished, so you can scroll down.
Now here, this term is resistance. Now we will see what is the resistance. What is the resistance? We will see.
Yes, sir, finished.
All of you finished?
Yes, sir.
So now we will see what the resistance is in the conductor in case of the wire. So resistance means you can say the obstruction in the path of anything. If I am going to a certain path and there are some obstacles in my path, then I can say that there is a resistance in the path. So resistance is uh, obstruction offered by any material in the flow of current. Resistance always opposes the flow of current in the flow of current. And the cause of resistance cause of resistance, I have already told you, when the electron moves in the conductor, there are ions also, and electron collide with those ions. And due to this collision, we have seen that due to the collision, there is a change in the momentum. Means there is a change in the velocity of the electron. I am not going in deep conversation of this, but I am just giving you the brief idea. The cause of resistance is the collision of free electron with ions. Cause of resistance is the collision. We know that the current is due to the flow of electron, and in the path of flow of electron, there are ions, and ions are the obstruction in the path of electron. So you can say collision of electrons with ions is responsible for resistance. And resistance is, R is the resistance, capital R. Resistance is the potential difference across the ends of conductor divided by the current. So you can write R is equal to V divided by I. And resistance is a scalar quantity. Resistance is a scalar quantity, and unit of resistance is, from here you can the unit of potential difference is volt. You can write from here, resistance is volt, and unit of current is ampere. Volt per ampere is a new term known as OHM, ohm, or we will represent this like this, ohm. So unit, SI unit is ohm. This ohm. So resistance is the obstruction for the flow of current, and the cause of the resistance is the collision of electron with ion. Noted?
Yes.
Yes, sir.
Okay, now we will see a resistance in a different manner. Till the 10th class, we know that resistance is potential difference divided by current, but the resistance is something different. Resistance in microscopic form. Microscopic form. We know that there is a relation between the current and the drift velocity. If here is a conductor and a battery is connected here, and the potential difference across the battery is V, so the potential difference across the conductor is V. And L is the length of conductor, A is the area of cross section of the conductor, N is the number of free electron in the unit volume of conductor, and Vd is the drift velocity of electron. There will be electrons in the conductor, and these electrons will move with the drift velocity, and V is the potential difference across the end of the conductor, and I is the current flowing. So we know that I is equal to area ANE and drift velocity. This is the relation between the current and the drift velocity. I is equal to NAEVD. I have I is equal to ANEVD. I am writing in this form. From here, we have A and E. Drift velocity, the formula of drift velocity, charge on electron into electric field divided by mass of electron. And here there is also the electric field due to this battery, due to this potential difference. There will be the electric field from positive terminal to negative terminal. And I have already told you this electric field is equal to the potential difference across the ends of the conductor divided by the length of the conductor. So I can write this I is equal to A small n, and this will become E square, and this will become E square, this will become M. And for electric field, I can write potential difference divided by length. Potential difference divided by length. Now I am taking this V in the denominator, so this will become ANE square by ML divided by ML, but resistance is equal to V upon I. So we will reverse this. V upon I. So this will become, this will up, this will go down. ML upon ANE square. And one thing more. VD, in VD you will write tau also. Sorry for that. We will write tau also. There is tau now. In VD we have E tau by M. E tau by M. Tau is the relaxation time. Tau is the relaxation time. So here tau will also come. Understood, guys? Actually, I have missed the tau here. Okay, is it okay?
Yes, sir.
Yes.
Okay. So V upon I, this will become ML divided by ANE square tau. ANE square tau, and this is the resistance. So I can write the resistance like ML divided by ANE square into tau. This is the microscopic form, means this is the resistance in terms of mass of M is the mass of electron, as is M is the mass of electron here, L is the length of the conductor, A is the area of cross section of the conductor, N is the number of electron per unit number of free electron per unit volume, E is the charge on electron, T is the relaxation time. T is the relaxation time. So this is another form of resistance. I have already discussed the symbols. What is M, what is L, what is A, what is N, is all. Writing M is the mass of electron and N is the small n is the number of free electron per unit volume of conductor, per unit volume, and tau is the relaxation time, or you can say average relaxation time. Relaxation time so from this equation, from the equation of resistance in the microscopic form, we can say that m is the mass of electron, m is the mass of electron, and mass of electron will never change. Mass of electron will never change. And charge on electron, this mass of electron, see here, R is equal to ml divided by ane square into tau. This mass of electron and this charge or electron will be same always, cannot be changed. So we can say resistance depends on here you can say mass and charge of electron is always constant, not always constant, but you can say constant here. Mass can also be increased, but that is not the part of your syllabus. If you are moving with the speed of light or with comparable speed of light, then the mass can also be increased of a body. This is with respect to the theory of relativity. So by the way, mass and charge is constant here. So resistance depends on, you can say this and this is constant. So I can say the resistance first R is directly proportional to L, the length of conductor. If you will increase the length of conductor, the resistance will increase. If you will increase the length of conductor, the resistance will increase, means the electron have to travel a longer path, and in a longer path there will be more number of collisions and the resistance will increase. Secondly, resistance is inversely proportional to area of cross section. If you will increase the area of cross section, the resistance will decrease. Why? Because when you will increase the area of cross section of the conductor, here if you have increased the area of cross section, more amount of charge will pass from the area in a definite time. More number of electron will pass. So you can say the resistance will decrease, or if you decrease the area, then the resistance will increase. And also you can see here this resistance in inversely proportional to small n. This resistance in it is inversely proportional to small n. N is the number of electrons, number of free electrons per unit volume, and this number of free electron per unit volume n, this changes with respect to the material. As the material change, the number of free electron per unit volume changes. So this is the property of material. This depends on the nature of material. Depends on nature of material. For copper, there are a different number of different n, and for aluminium there will be different n. Nature of material. So means n is the property of material. And one thing more here, this tau resistance is inversely proportional to tau. Tau is the relaxation time. Tau is the relaxation time. If you will increase the relaxation time, if you will increase the relaxation time, then the resistance will decrease. So, and relaxation time, I have already told you is related to the temperature. Relaxation time is related to the temperature. If you will increase the temperature, what will happen? If you will increase the temperature, the electrons will get the thermal and more thermal energy, and the collision will become fast, and time for relax of electron will decrease. So means the relaxation time will decrease. So on increasing the temperature, relaxation time will decrease and resistance will increase. So note it down or noted already.
Sir, finish.
Matthew and Naval.
1 second, sir.
Okay, you can take your time. So this in this way also we can determine the resistance in terms of length and m a tau. Tau is the relaxation time, and relaxation time is changing with respect to temperature. As you will increase the temperature, the number of collision will increase due to increased energy of electron, and the time as the collision become fast, the time for relax of electron means the relaxation of electron will decrease. You can say the relaxation time will decrease. If the relaxation time will decrease, the resistance will increase. A is the area of cross section, M is the mass of electron, L is the length of conductor, V is the potential difference across the ends of the conductor, E is the electric field generated, tau is the relaxation time, E is the charge on electron, N is the number of electron per unit volume of the conductor. So you should also know this formula of resistance. Resistance is equal to ml upon ane square tau, or you can also say resistance equal to potential difference divided by current. Should I scroll down?
Yes.
Okay. Now you can note down if you have not written. Anyone? Is it okay now?
Yeah, okay, sir.
So you have to relate all the things with each other. How the resistance will change when the length is changing, area is changing. So resistance can be written R is equal to ml divided by a n e square into tau, or resistance is also potential difference divided by current. And if you fix the material, then n will automatically fixed. If you take a copper conductor, then n is fixed there, because n depends on the material. If you once you have fixed the material, means n is fixed.
Done, sir.
Done. Okay. Nawal, completed now? Okay. So so the next term is the resistivity. Oh, sorry. So next term is the resistivity. 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 And this resistivity I will represent with a rho. This is rho. And resistivity is the property of material again. Resistivity is the property of material again. So resistivity is independent of length and area. This is independent of length and area. Suppose if you have a copper conductor of length L and area of cross section is A, and after that you take a copper conductor of length 2L, and the length is also doubled and cross section area. These both are the different conductor, not the same. So here the if you increase the area 2 times, so resistivity of this rho 1 and resistivity of this rho 2 will be same. This is not P, this is rho. This is something like this. So resistivity does not depend on the length and the area. So we know that the resistance is directly proportional to length, and also we know that resistance is inversely proportional to area. Now I can write resistance is directly proportional to L by A, and when you will remove this proportionality sign, you will get this resistivity rho L divided by A. rho L divided by A. So this is the resistance can also be written in this form. Resistance can also be written in this form. R is equal to rho L by A. Rho is the resistivity, L is the length of the conductor, A is the area of cross section. Now if I want to calculate rho from here, so I am putting the value of resistance. Resistance is ml upon A and E square into relaxation time is equal to rho L divided by A. Now you can see here A is cancel out and L is cancel out. So you can write here rho is equal to m upon ne square tau. M upon ne square tau. So rho can be written in this form. So see here rho is only depending upon the means material. So please note it down.
Sir, can you scroll down?
So see here the this resistivity is independent of length and area. Independent of length and area. So from here you can write independent of length and area. This is the resistivity. SI unit of resistivity SI unit of resistivity. You can calculate the unit of resistivity from here. From here, you can write RA by L. Rho can be written as RA divided by L. Unit of resistance is ohm. Unit of area is meter square divided by meter square. So the unit of resistivity is ohm meter. This symbol is ohm. OHM ohm. SI unit is ohm meter. Ohm meter, or you can also write this as ohm meter. And for the definition of resistivity, I will take the cross section area as 1 centimeter square and length as 1 centimeter square. Then that resistance will be the resistivity of the material. Note it, all of you.
Yes, sir.
Yes, sir.
Nawal.
Yes, sir.
Okay. So you should also remember this formula also, and you can derive the resistivity from here. Put the value of resistance ml upon a ne square tau, and you will get the answer. So what I am doing now, if I am taking a resistivity of if I have this formula, resistance R is equal to rho L divided by A. If you have taken area, you have taken length of the conductor as 1 meter square and area of cross section as 1 meter square, then this is 1 and this is 1. So resistance equal to resistivity. So you can say resistivity is resistivity this time is the resistance. This resistivity this time is the resistance now. Resistance if someone is saying define resistivity, then define the resistivity in this way. Resistivity is the resistance of conductor having unit length and area. Unit length and unit area of cross section and unit area of cross section. Area of cross section. And see here we have the resistivity as rho is equal to m upon ne square tau. We have rho is equal to rho is resistivity m upon ne square tau. Ne square tau. See here m upon ne square tau. So rho is depending on mass, rho is depending on charge, and we know that mass and charge of electron is always constant. So rho is inversely proportional to n and inversely proportional to temperature. And n is the property of material, and tau is the property. Tau is changing with temperature. So you can say resistivity is depending on the nature of material as well as the temperature. From this formula you can say resistivity depends on nature of material and temperature. Nature of material and temperature. Why temperature? Because tau this relaxation time is depending on the temperature. So note it down.
Yes, sir. Finish.
Yeah. All of you, please note it down.
No, sir.
Okay. Matthew, completed?
No, sir.
Very good. So we have just completed the Ohm's law, and firstly I have told you relation will be the current and the drift velocity. Current and the drift velocity, this is the relation. What is Ohm's law? Ohm's law is this, and graph of Ohm's law, and after that what is resistance, and after that I have written resistance in terms of mass, length, area, and this and this. Now the resistivity. Now there is a term conductance. There is a term conductance. Now resistance, conductance is the ability of a conductor to conduct the current, and resistance is the ability of the means you can say the property of the conductor to oppose the flow of current. Means conductance and resistance are just opposite. Conductance is represented by G, and this conductance G is inverse of resistance. Inverse of resistance so I can write G is equal to 1 by R, and the SI unit will be 1 upon ohm, means ohm inverse. You can write ohm inverse or ohm inverse. Or also this is written the unit of resistivity conductance is MHO. OHM, MHO, reverse of this. So you can also write the G in terms of G is equal to 1 by R, and we know the formula of R, ml upon ANE square tau. Now there is a term conductivity. Conductivity is represented by sigma. There is one more sigma there was one more sigma, surface charge density. This is another sigma. This is the conductivity. Conductivity is the like we have resistivity. This is the reverse of resistivity. This is inverse of resistivity. So sigma is the resistivity, and this is inverse of 1 by rho. Rho is this is resistivity rho, and the unit of resistive conductivity is SI unit. I am writing ohm inverse, meter inverse. And for resistivity, you can write in terms of N E square tau divided by M. M upon N E square tau by earlier resistivity. Now the reverse of this. Now there is another term mobility. Mobility is related to the motion of electron. Mobility is the ratio of drift velocity and electric field. Drift velocity and electric field. Drift velocity and electric field. And this is represented by mu. This is represented by mu, and this mu is the drift velocity, ratio of drift velocity divided by electric field, and drift velocity is E into electric field into tau by m, and divided by electric field, and electric field is cancel out, so you will get E tau by m. So mobility is E into relaxation time divided by mass of electron. M is the mass of electron. There is another term, current density. Current density. Current density is current per unit area. Current divided by area is known as current density. Suppose this is a conductor, and this is the cross section area of the conductor, and I current is flowing like this. I current is flowing like this in this conductor, and A is the area of cross section of this conductor. So current density is represented by J. This is J, I, J, K, J. So current density is the current flowing divided by area of cross section, and from here you can calculate current also. I is equal to JA. And this J can be uniform or can be non-uniform. Uniform means not changing with cross section area. J can be uniform throughout the cross section area. But there can be the cases where the J is non-uniform. So if J is non-uniform, then you will write current is equal to, you will integrate getting my screen, Matthew?
Yes, sir.
Fine. So this is I. So you will integrate on both sides. When this is non-uniform, you will write J vector into dA vector. And current density is not a, this is like current is a scalar. Current is a tensor, but we consider current as a scalar. So here this current density is a vector. It is vector and direction is same as that of current. As that of current, I is current. And the SI unit of this is SI unit of this ampere meter square, meter inverse. If this is non-uniform, okay. So SI unit is ampere divided by meter square, or you can write this ampere meter to the power -2. But you should remember this point. Usually in NCERT, J is uniform. J is uniform. Usually in 95% cases, you will get J as uniform. If J non-uniform, then current can be calculated as integral of J vector and the area vector. Area is a vector or a scalar, Matthew? Area is a vector or a scalar?
Scalar.
But I have written here the area vector. Why? Actually, have you studied the Gauss law and all that in electrostatics? Electric flux.
Yes, sir.
In the electric flux, for defining the electric flux, we take the area as a vector. There is a topic there, area vector. Hope.
But this is area, right? Not area vector.
Yeah, this is the area vector. This is the area vector. Okay.
Okay, sir.
Yeah. Please note it down, guys. Actually, this is the theoretical part. I think this is very easy. You have written this.
Definition from current density onwards.
Uh, uh, Please all tell me from where you want to note it down.
Current density onwards, sir.
Current density, sir.
And Nawal,
Current density.
very good. This is, I think, easy chapter as compared to the electrostatics. You have to just relate the things, nothing else in this chapter. Relate the things, relating the formula with each other. How many of you know about the Gauss law? What is Gauss law in electrostatics? Have you remembered what is Gauss law?
It's like electric flux in an enclosed surface is equal to the total charge by
Very good.
the electric
You are
constant,
right.
epsilon zero. Yeah.
Yeah. Means if you are placing a charge Q inside a closed surface, closed, then the electric flux, this phi is known as electric flux. This is a charge divided by epsilon. Good. So written now?
Yes,
Written.
sir.
So now we have the Ohm's law again. We have Ohm's law again. See, instead of current, now there is current density. This is cancer. This is the vector quantity, and potential difference is the electric field. Potential is a scalar, and electric field is a vector. And resistance is resistivity, rho. These terms are related. I am not saying these terms are same, but these are related. Means here is current density, here is potential. Sorry, potential difference. There is a electric field and resistance, resistivity. So now we have microscopic form of Ohm's law. Ohm's law. So microscopic form of Ohm's law is we know that so microscopic form of Ohm's law is written like J vector is equal to sigma. Sigma is the conductivity and E electric field vector. This is the microscopic form of Ohm's law. So in Ohm's law we have current, we have resistance, and we have potential difference. So you can think this like J is like current something. This is not the current, but you can think if you want to learn this formula. And electric field is potential difference, and resistance, this is the conductivity. Conductivity is related to resistance, inverse of resistivity. So this is the Ohm's law in the microscopic form. So J is the current density, sigma is the conductivity, and is the electric field. Now, if length of conductor is increased by 2%, by 2%, by 2%. Calculate percentage change in resistance and resistivity. Calculate percentage change in resistance and resistivity. So they are saying we have a conductor earlier, and this conductor have the length L. I am supposing L is the length of the conductor initially. A is the area of cross section initially, and rho is the rho is the resistivity of this conductor. Rho is the resistivity of the conductor, and they are saying that calculate the percentage change in resistance or resistivity. We have the formula of resistance, R is equal to rho L divided by A. We have this formula. So if I want to calculate the resistance of this conductor, what is the resistance of this conductor? So resistance of this conductor will be rho L divided by A initially. And now the length is increased by 2%. What is the meaning of length increased by 2%? Length increased by 2% means earlier the length is L, now increasing the length by 2%. 2% means 2 divided by 100. This is the meaning. This is the math. If I am saying I am increasing the length 50%, means length is increased by 50% divided by 100. This is increase in length by 50%. You can say this is as 50% increase in length. Increase in, this is 2% increase in length. So now finally same conductor we have, but this time the length is decreased, sorry, increased. And you can imagine if you will increase the length, the cross section area will decrease. If you will not, like this is a pen, this is a cylinder, this is a cylindrical conductor. I am taking here also a cylindrical conductor. If you will increase the length, you have if you have a you can say if you have a wire, if you will stretch the wire, the length of the wire will increase, but at the same time the area of cross section of the wire will decrease. You will see this. So finally the length will increase by 2%. Length is increased by 2%. Now final length, this is the final length, I am supposing this. Finally length final is L plus, this will become 0.02. So this will become 1.02 times of L. Length is becoming, now this time the length is 1.02 times of L. 2% increase length. Now we don't know how much area will decrease. So I am supposing area as A dash. Now length we have, and you can think that the volume will remain same. Volume will not change of the conductor. Volume will not change. If you will stretch the wire for increasing the length, the volume will remain same. Volume will remain same. Volume will remain same. So volume initial, what is the volume initial? Area into length. Volume initial equal to volume final. This is volume initial is equal to volume of conductor. Finally volume will not change. So initial volume is initial area into length, initial length. Final volume is final area is A dash into final length. Final length is 1.02 times of L. Now from here this L is gone with this. Now we have final area. A dash is equal to A divided by 1.02. This is the final area we have. This is the final area we have. Okay. Now they are asking the percentage change in the resistance. So always remember that percentage change is the total change is in resistance divided by the initial resistance. I am writing percentage change. This is mathematics actually. Percentage change in resistance R is equal to R final minus R initial divided by R initial into 100 into 100. And R final is, when you will calculate R final, rho L divided by A, we have the formula of resistance. Rho is same. Rho will not change because the material is same. I have told you rho will not change if you will increase or decrease area or length. So resistance here is only depending upon length and area. So R final you will take final length or area final area. So this will become final means rho and L final divided by A final, and this is minus R initial rho L initial divided by A initial. I for initial, F for final, and this is divided by R initial. R initial is rho L initial divided by A initial. So from here rho and this rho, This is not R, this is rho, will cancel out. This row will cancel out from here. So we will have L final by A final minus L initial by A initial divided by L initial by A initial. Now put all the values, and this is also multiplied by 100. This is also multiplied. L final is, actually time is over now. L final is what is the final length? 1.02 times of L. Area final is A upon 1.02. A upon 1.02, and this upon will come here 1.02, and this will become, this is L initial L by A, and this is L by A, and this is multiplied by 100, and L by A is cancel out from everywhere. This L by A from here, L by A from here, L by A from here. When you will calculate, you will get the answer 1.02 square minus 1 into 100. So you will get the answer 4.04%, and percentage change in resistivity is 0, because there will be no change in, if percentage change in rho will be 0, mean no change, because the resistivity will not change. Okay guys, so please note it down and hurry up.
Yes, sir. Finish.
Done, sir.
Matthew and Nabal, have you got this?
Yes,
what
sir.
I have done in this question? Actually, I have done nothing. I have just read the question, and I have done the things according to the question, like increase the length by 2%, and after that I have just used the formula only. Okay guys, now you can leave, and wait, fine.
Thank you, sir.
Okay. Hello, Akash.
Hello, sir.